So, Ashwar, do you want to get started or probably wait for people to join in?
Yeah. Let's only start. Let's give like at least 3 more minutes, so you can start at like 9:10.
Mm, yeah. If anyone wants to give an introduction, feel free to,
Yeah,
yeah.
Jay, do you want to also stick if you have a presentation? Can you stick it in the Discord group?
So I don't have a presentation. I had basically just annotated the paper. I will just share this paper probably in the Discord.
Okay. Okay. Cool. Cool. Yeah. Maybe you can also share
Yeah,
this.
maybe let me just share that as well once in the Discord before we start.
Sure, I'm happy to introduce myself. Sorry, I was talking on mute there. So. Everyone hear me?
Yep.
Okay. Yeah. So my name is Steven. Nice to meet everyone. My background originally, I guess, is in physics and mathematics. I transitioned to machine learning, data science. I guess right after grad school. So I've been working in industry for a while, and research whenever I can.
Cool. Nice to meet you. Where are you from? Around?
I guess. Oh man, I've been all over the place. I was living. So I'm currently in the Midwest, but I was living in Palo Alto before that.
Palo
Just a
Alto
few.
in like Cupertino? I mean, not Cupertino. In California?
Yeah, in
In
California.
California.
I lived in San Francisco and then moved down to kind of the Silicon Valley area for a while, and basically lived there until COVID, and then everyone left, and so there's
You
like
went
no
to the
reason to be
Midwest.
there
Interesting.
during COVID, and so we all left. Yeah, and I haven't gone back yet. So
Where in
Cool.
the Midwest are you from?
I'm in Columbus right now,
Oh, okay.
Ohio.
Gotcha. I'm in northern Indiana.
Oh, really? Okay, yeah. It's all really close, so you know, if you want to get
Cool. Cool. All right. I think
So,
there's a few new people. Mala, Justin.
yeah.
If you want to
Hey,
just do one line.
yeah, my name's Justin. Nice to meet you all. I'm a PhD student at USC, ISI. I mainly work on dialogue systems, but of course, obviously, generally interested in all NLP problems. So nice to meet you all.
Very cool. Nice to meet you too.
Hey, hi, this is Praveen. I'm actually from India. I'm working as a data scientist back here itself. Yeah, that's about
Cool.
it.
Anyone else who's here for the first time?
Yeah, this is my first time here. Pretty cool. Like you guys keep up doing this.
Thank you. Do you want to
Okay.
do a
Yeah, I
brief
think.
intro?
Yeah,
Yeah.
Renan. I study on University of West Florida, and I made a little company that does these things with NVIDIA. And I don't know if I comment on the chat and like Papa Chuck. I'm trying to put together like an avatar to speak like a virtual assistant, and this is pretty cool. Like I always look for these ways to cram as much as I can on a single GPU, because when you do the cluster, that's money. You know, like being optimizing it is cheaper, make more profit.
Yeah. Cool.
Yes, I think,
Good
yeah.
segue. Do you want to get started, Jay?
I think I can get started. So I've shared the paper, annotated paper as well on the Discord. And yeah, so maybe I'll just get it started. So as the name suggests of the paper, right? So at least that's what it's trying to do is like how much can you, let's say, push the model performance by making optimization and tricks on basically, let's say, vanilla transformer and train it for a single GPU on a single one day, like basically 24 hours of training, just that's it. So at least in terms of if you look at, right, in most of the landscape of language models so far, most studies are focused towards like scaling up, and at least this papers take somewhere a bit more 180-degree turn, and at least tries to go the other way around. So like basically, like with, let's say, the scale down architecture similar size of BERT, how much can you like basically cramp up like the knowledge in the model and also push the limit of the model. So that's one interesting thing, at least why hey, this is important. And maybe also one more thing, right? That as the smalls keep on growing bigger and bigger, right, they're inaccessible. So by making the smaller, and also like optimizing, like basically based on scaled down versions. It would basically make research more accessible. So that's one other point. And at least one maybe, so there are a couple of studies which goes around, like let's say scaling down, or at least trying to show that you can, let's say, with like small model size also try to get the good performance. But still those are also somehow like maybe they also have some shortcomings or advantage disadvantages maybe, or limitations. So for example, chinchilla was the one which shows that when you, let's say, have, you can reach like GPT-3 performance with just 70 billion parameter. So it's like maybe 175 to 70 billion by just training for longer. So basically, you need to train the model for like more number of tokens. But in this case again, there's an issue of like scaling up the data itself, right? Which again makes it very inaccessible. The other part being instruction tuning, which is at least more, which has more shown to improve the model performance. But the problem with instruction tuning is that like at least getting this data maybe at certain scale or at least sufficient reasonable scale is still a challenge, because yeah, it is more usually used for fine tuning and not for actual pre-training paradigm, at least right now. Maybe in the future it might be used, and maybe then we might be able to still get push the model performance further as well. But that's like one of the shortcomings of instruction tuning, to be honest, right now. So in this paper, what they try to do is they pick out the BERT architecture itself, and maybe and it's very standard vanilla transformer with just few modifications where activation is ReLU instead of JeLU, and they make some tricks and basically optimizations over it to actually improve the model performance. So it's more like a empirical paper where they try to investigate and understand the use of different components, and maybe by, let's say, eliminating what operations or like basically gradient computations, we can still get the same performance without compromising on the model yeah, and also like within 24 hours span. So here if we see, right, at least in terms of the analysis, so uh, at least scaling is hard, that's pretty true. And there are three axes across like this where it goes. So one is like compute, nexus data, and third is model. So in this direction, what they try to do is like in terms of data, they don't do any scaling. So it just like have as much data as possible. They just make it like that's one. Probably compute is the one direction where they try to like scale down like a lot. And model also, it might be considered as a scale down because sufficiently we just go for BERT, whereas the scaling laws and other model like basic studies have like explored much higher model sizes. So yeah, that's the high level idea, or at least like I'd say the TLDR of the paper. So it could be like in one way summarized as like a sort of a toolkit of tips and tricks that you can use like to make your, let's say, LLMs like basically train faster and also like more efficient as well in terms of like training and like ramp up more knowledge into them so that they are accessible to everyone. So yeah, feel free to interrupt if you have any doubts or anything at any point of time.
So they didn't experiment with any big models.
No, they don't experiment with big models. So the goal is to like probably use BERT, similar architecture as BERT, with just very minimal modification in the architecture. So the overall architecture is still same, and they just want to like basically see how much closer they can get to the BERT performance or even beat it. That's
By reducing the BERT model size.
no, not reducing the BERT model size, but like so in a way, what they do is they reduce certain operations in the forward propagation, which then again effectively reduces the backward computation, like the gradient computations, and that speeds up the training. So for example, right, biases are there one possible way. So they remove biases, and like that kind of reduces the gradient computational cost, right? Like you see when you do back prop, but effectively you still get same performance like in a way, and also speed up in the training. So that's one like one possible changes that they have made. But I'll also highlight more changes as well, and maybe whatever their suggestions like were in terms of what might be the possible way forward to go.
Yeah,
So,
sure.
yeah. So that's one. And yeah, like as I said, right, like typically architectures have grown more and more with time. And yeah, like also touching on the same idea that instruction tuning is useful, but still training might be currently not accessible due to like low data scale of the actual training data. The instructions are like not mm, probably to a certain scale as we expect in pre-training paradigm. So yeah, that's one. So probably in this case, as I mentioned, right, they pick out the BERT on paper only, and then just make the modifications on top. And at least BERT, why they chose BERT was like one prominent reason being that it was the first architecture, right, which shows like the effect of the transfer learning as well. And they want to basically just like see with this first simple architecture, how much can you push the performance with like very minimal modifications. Like, you don't want to like modify things or at least add certain components which we know like have maybe let's say advantage in terms of performance gains. So that's not the objective here in this study at least per se. And yep, so that's TLDR basically in this case what downstream performance can be achieved by a modest researcher when training from scratch with a single GPU on a single day. So at least in one way or the other way, we can think of this paper as similar to the emergent abilities of language models, right? So in emergent abilities of language models, what they try to discover is like at what parameter size, let's say you see some like emerging behavior out of the model, which basically help like let's say lead to better generalization and better performance. So in a way, you're also, if we look at in a similar perspective, it's trying to typically answer out what sort of tips and tricks you need to add into the standard BERT or like basically like language model pre-training to actually like let's say get the same emerging abilities in terms of faster training convergence as well as like more better performance with limited compute. So that's one. Probably like yeah, they do highlight that this question is still more an interesting open-ended question between existing and new pre-training tasks. But at least one paper that I can recall where probably this is a bit expert, I would say, is UL2, where they try different sort of objectives and show the effectiveness of those objectives in terms of the model performance. So one being mixtures, uh, denoising mixtures objectives, so where they have different like denoising objectives like so BERT like MLM like mass language modeling being the standard one, and many more beyond that as well. So maybe feel free to check out the UL2 paper from Google.
What was UL2? Can you just give the full form?
Which one? This one, UL2.
Yeah. Mhm.
Unifying learning. I think. Let me just drop the paper link. Yeah, unifying language learning paradigm.
Okay. Okay.
Yeah. So at least they go for more scale, but at least like their study is more towards like which sort of objectives works and which don't, and they do more extensive analysis of like this, and at least try to highlight like the importance of different pre-training tasks in terms of model performance and generalization. So that's like the idea there, at least. And in this case also, at least like to a certain extent, right? So this study also is somewhat being influenced by scaling laws. So scaling laws like came by Kaplan and Kaplan et al. And basically their point was that as you keep on increasing the model size, right, your performance like basically improves, or at least in another way, loss gets reducing, right? So there's so basically this power law relationship that happens when you like basically go to a scale, like to infinity in a way. So in this case, what they say is like basically that still scaling laws effect still holds true, right? In this case as well. And as you go towards the other side as well, right? Like the scaling down paradigm, it becomes very, very hard to probably have this good performance gains with very small architectures, basically. So one way that maybe let's say you can do this thing, right? Like at least like maintain, let's say, good performance as per scaling laws is have the same model size, but still like maybe speed up in terms of the gradient computations by reducing unnecessary operations, right? Or at least like maybe like eliminate some redundant operations that do not contribute to your model learning, sorry. So by that, you can speed up the gradient computations and still having the same model size and maintain the performance, or at least have nearly constant performance like across as per the scaling law. So that's what the paper is trying to do in this as well scenario. So just before we start and like understand the probably let's say the setup and what maybe like importance of different components, first let's just understand what the basic setup looks like. So they just pick out a transform-based language model, and this is similar to the vanilla or BERT you can think model. So that's the one. And they just like use the MLM objective in this case. So where MLM being very simple objective, and they just try like use that, and they train it completely from scratch. That's the one point. So like no pre-trained models is used in any part of the pipeline. So maybe in let's say distillation or at least like there's nothing as such happening in this. And you can use any let's say pre-training data that you want to use. Like you have just only one constraint that it shouldn't be a part of downstream task, or there should be some sort of dedupe, like at least. Next is in this case they use pre-trained tokenizer from BERT itself, like the one. So that's like the only pre-training component out there in the this sort of entire setup or like we see paper. And they train like only for 24 hours. So this 24 hours include both. So like we see like the actual pre-training as well as the downstream fine tuning. And in terms of downstream fine tuning, that is pretty much limited because they want to actually understand how much gains you get from pre-training itself. So, is there any question? Yeah.
So just a quick one. So how many parameters could you achieve in 24 hours for each of these GPUs?
Sorry, I didn't get. So you mean parameters, right? So I think for this model that they use, right, like or try, this is BERT standard BERT model. So it is I think 440 or something million parameters.
So
Does
in
that
24 hours on the 2080, you got like what, 40 million parameters?
no, so not 40 million parameters, right? So this is like a 440 million parameter model that they have, right?
Yes.
So they just train that on 2080 Ti. So it's not like basically like a reduction or scale down version of the model. That like does that make sense or probably so what they are trying to do is not like take a bigger model and like basically get a small model version of the same model. They are like using the standard BERT model and just trying out this different tips and tricks on top, such that you can basically push the training and like basically the model performance further with just like this simple GPU. So they are not like basically um, like getting 40 million parameter or what in this case. Does that answer your question or Renan?
Yes, it's good.
Yeah. So that's there. And for the others also, it's the same one, $5 or less. And in this kind of study, they try two GPUs mainly. So first is like basically this classical like RTX 2080 Ti. So I think this GPU came out before BERT paper itself. So that's the one. And then they try out like the ones that were released like more recently, probably after the BERT. So they are the GPUs are a bit much faster, but yeah, essentially they still clock like the performance across 3 and like C. And their settings is 4 CPU cores and just 32 GB of RAM, which is at least comparatively much lower than the other model training like code or at least the setups that we see. And in this case, uh, the optimal architecture of the transformer is not fixed as such particularly. So the optimal architecture in the sense that they are like specifically interested in just like understanding how much like BERT can get like with the same compute, like limited compute. So they don't like explicitly like put specific optimal architecture which might like lead to better performance. So that's one of the point they like explicitly like avoid because they want to like not then it becomes very difficult to understand where the gains are coming from. So is it like this use of specialized architectures or modules that are making that like resulting in a gains, or probably the actual training procedure in a way? So that's one like in a way. And at least if we look at the time durations, right? In this case, all of them are pretty like requires a lot of like time to train, and all this are like on TPUs, like so TPU core slices basically in a way. And this is just on a single GPU. So yeah, understand the scale and imagine like how much reductions they are able to do while maintaining or near the similar BERT performance. So just to give you a context, BERT was like standard BERT was trained on 16 TPUs, that is 4 days. And I think this is like probably 15 or 20x smaller than the one. Yeah, something like that roughly. Yep. So is this anything important? Yeah. So also one more thing, yeah. So in this case, in BERT also they do, I think, maybe include this different downstream task in the pre-training procedure at the very end. But in this case, I think they completely exclude those and they just introduce like this downstream data sets during the fine tuning only. in order to avoid any bias in the performance estimates, probably, or at least understanding how much you can cramp up in the training. Yeah. So there is one similar work I would say which is important at least, but which also tried to do very similar thing. So what they do is like they train a BERT large model on like let's say sequence in the 128. In this paper also they go for 128, and they train on a full server node, so with 8 300 GPUs. But here the difference is that they go probably one only one GPU. So I think so probably from this setup it's 15 times smaller. But I think if you compare this setup, it is like way smaller. Yeah. So that's one point to highlight. And yeah, I think apart from that, there are other studies which have done this, but still those are more or less like still you're using entire server node, or at least like so which is like a complete compute full server, and like this goes for just a single GPU. So that's the difference at least I would say. And in most of the studies that are focused, let's say, on efficient transformers, right? So there is like maybe one way you could make transformers efficient is like probably let's say you make some modifications in the attention calculations that speeds up the computation. So that's one. So where with implementation of efficient attention mechanisms. Other than that, maybe there are some other mechanisms, probably in positional embeddings, or maybe like reducing the feed-forward network parameters as well, at least some additional changes on the top. But in most cases, if we look at like at a macro level, we don't see much improvements probably, uh, or at least like the improvements, or like we see the suggestions that modifications are out there. Those are very minor and maybe like not significant in the performance updates like or gains that we might have expected. So that is one thing, and like people have not much explored in terms of what else could be done in terms the architectural modifications as well. Yeah. And scaling laws also, just to give you context. So the model size like counts to the actual model parameters excluding the embedding layers. So because I think in typical most of the setups, if you look at embedding layers do constitute for sufficient portion, but so we exclude those like parameters and like our calculations, and we just consider based on the entire other model parameters that are a part of the one in this case. And yeah, that's probably for this. Any questions so far? Okay, then I'll move forward. So yeah. So now in this case, like the implementations, right? So as I mentioned, right, that they do not introduce any special components, and they just rely on the standard PyTorch framework for the implementation. And this one I need to like read a bit more. I'm not sure about efficient attention kernel. So this is more like once they choose the architecture, then they enable this. So probably I'll update on the Discord channel once I read a bit more and have more clarity on this. And they use mixed precision like from the standard PyTorch like framework. And overall, if we look at the ones which are highlighted in the gray area, so those are things that they tried out but didn't work out at least. So probably if we look at like see based on different like bit floats and scale bits, right, or at least B float operations, let's just see, they don't see any gains in model training, which typically like at least in the past have been known to. So that's one. And also for the data, they use like Wikipedia and I think probably Pile as well as the English book corpus. So that's the three data sets I think they prominently use in the model training. And one more thing for the one in this choices, right? So one is like there is one change. So for example, in first change that you would have is like based on the vocabulary, right? So whether like let's say BP or like WordPress, which one like maybe leads to better performance or something. So probably based on their analysis, they found that in terms of the tokenization approach, nothing like changes a lot, and like the changes are not like much significant. But when you change the vocabulary size, the model performance is highly variable. So it's just like the higher the vocab size, the better the performance is. So probably if you look at the standard vocabulary size, there we find more optimal, let's say, performance. But if you again improve like beyond that as well, then probably you don't see much gains compared to the improvement or at least the, let's say, increase in the model memory at least per se. So that's one thing to highlight. Apart from that,
So they're not making changes in the architecture. They're just saying, checking if what changes they get through BP or any other vocabulary. Um,
yes, yeah. So they are not making changes in the architecture. I would say like the major changes. We'll see some of the minor changes in terms of like the architecture probably later on. But as far as the transformer architectures go, right? So they don't touch like maybe attention blocks and maybe change this completely or like yeah. So the attention blocks, multi-attention, feed forward layers, those are very similar only. It's just like maybe let's say the layer norms are different. So maybe placing of layer norms, right? One pre and post norm. So that's one which I would talk about, and probably many studies have also shown. Apart from that, I think this query key. So this the biases are like in different modules and like what speed ups maybe you get based on this biases probably later on during the downstream task, right? Like if you have like attach a linear head, right? So what happens like when you do the, let's say, some changes in the linear head, so that's one like I would say setup. And here they try to see like in terms of the embeddings, like do they see any differences when they switch from one tokenization scheme to another. So that's one. And as per the setup goes, right? So it's 128 that the like sequence and they go, and they just use the same setup as BERT, where they pack the sentences with like uh, separator token. And yeah, and one of the studies or at least like things that they show, and which is I think are also pretty much known from Vision, that adding CLS token doesn't make much difference in the pre-training, like to be honest. And that's what they have also found. And I think first paper which tried to point out this was VIT, I think. So Vision.
so essentially, the TLDR of this paper might be like how much can we get performance of the original BERT in a single day, right?
Yes, yeah, that's yeah.
Mm.
How much performance you can get from both in a single day by making some modifications in the uh, training and the architecture, but those are pretty minor modifications.
Okay.
Yeah. And for batch size, I think they use micro batch sizes with gradient accumulations, and like yeah, they just run a single epoch training because like yeah, like limited compute and the data is lot, so yeah, it just like a single epoch. Now let's come to modifying the architecture, right? In this case, as we discuss or like if we saw. So probably if we see right in this case, like uh, intuitively, if you think like having smaller models will be optimal, like let's say when we go for like probably low cramming regime or at least like trying to like pack everything into like this particular model with like minimal compute, right? So that's one case. But probably if you look at the scaling laws I mentioned, right, there is still this token level efficiency that you have. And that law at least indicates that the model performance is highly variable depending on the model size, but not the architecture like type of the transformer that you use. So maybe whatever architecture, let's say you use of the transformer, right? More or less at the end of the day, you will get like nearly similar performance if your model size is very similar. So whatever variants you go for, you will get roughly same like performance at same scales. So that's like the one gist and probably why they also like stick to the standard architecture of the transformer in a way. Next is smaller models, let's say might be so one advantage with smaller models if you go right, so they might learn effectively faster and maybe let's say probably, but there's still one, there may be two problems, right? So one is like there would be capacity bottleneck happening, right? So how much can you over parameterization if you see in the standard like most of the research nowadays, right? Over parameterization tends to help much better, and probably the performance in this case like might not justify the throughput gains that we get, right? Because at the end of the day you have this capacity bottleneck happening. So yeah, they just try to see in this case, and as I mentioned, right, scaling laws here still hold true. Next thing in this case, if we go about, right, so let me just see. Yeah. So one thing that they see for based on all of the architectures, or at least they try out, like different architectures are unpredictable, like during the initial state of training. So when you like start with the training, right, all of the architectures, like basically we cannot predict the trajectory, or at least those are more maybe their behavior, or at least the way how much we can pack, right? Like basically would be more evident once we let's say pass the first billion tokens. And then as per their analysis, it seems that performance is like just a multiplicative constant, like the differences in between efficiencies that you get. and this constant only depends on the model size in this case. So which again justifies that you just need to maintain the same model size without maybe by like, but with like let's say still reducing the gradient computations in the for backward flow of backward prop. So that's one. And yeah, so when we look at the different things, right, the scaling ones. So if you look at different things or like maybe what was, and one of the other evidence which shows that performance is slightly coupled with model sizes, like let's say they try out this funnel transform architecture, they drop FMA feed-forward network layers, use recurrent layers, or train with back propagation through time. So like unfolding and having the same effect as recurrent networks. So all of this doesn't seem to probably help in way in the improving model performance because effectively you're reducing the model parameters in a way. So which again, if like shows or at least high brings to the same point that yeah, you need sufficient model scale at least to a certain extent for a good performance. Next is in this case, yeah. So if you look at right, so they also typically go to the same point, right? So maintaining the same model size, but still reducing the number of operations that can be done, right? Speeding up the computation. So probably one simple intuitive way or obvious way would be to just disable the biases that are there in the model, all the linear models, and probably see what impact or like effect you have on the model performance. So if you look at the attention, right? So in attention, they disable all the biases in the uh, uh, query, key, and projection matrices that are there at the start and the end. So once that's there, and after that, if we like basically there are other options as well they can do. So one is like probably let's say you update or at least optimize the softmax operations. Those are at least computationally more expensive as well as the scale dot product operations. But based on their um, analysis, it seems that they don't provide any benefits in terms of like basically when you add or basically uh, have like this efficient attention mechanisms. Apart from that, you have this rotatory embeddings. Like I don't know about much details of this embeddings, but at least this is a different way of embeddings. And when you add this, you see some gains, but these gains at the end of the training like are merely evened out, so you don't see any like significant gains in this case as well. So effectively, you have no impact of having this as well. Next is like when you have feed forward blocks, right? So this is also again from empirically finding out that like removing all the biases like tends to work better. Next is in this case again that you keep the same traditional standard feed forward network as observed in the attention paper, and like only one change that helps is like basically changing to the activation gelu rather than relu, and that's one case. Probably they see a small improvement uh, in let's say gated linear unit. So gated linear units. Let me just maybe pull. I think if someone is not familiar. So for any doubts, maybe let me know. Like, is this diagram visible? Okay. So yeah, gated linear units are nothing but let's say you have the same activations in same like embedded representations maybe. You take the sigmoid of one and then basically apply a gate over towards it. And traditionally, what the approach was is something this way. So where you slice the embedding representations in halfway, and like you use the half like slice version of the embeddings to gate like the other one. So that's how the gating works in this case. And it basically essentially decides like the flow of information like from each neuron, like how much would be the flow of information. That's the simple gist. And yeah, so uh, they do not like when they like reduce let's say this gating linear effect, right? So they do not increase the parameters of the feed forward layer in this case, but they still are able to like see improvements. So let's just suggest maybe if you go a bit smaller scale comparatively, which is like very minor, then probably you don't see much difference in performance. Apart from embeddings, feed forward block, in terms of embeddings, they found that scaled sinusoidal embeddings have much better impact over the learned or like basically unscaled sinusoidal embeddings that are out there. So that's like the other finding. Pre-norm like helps than the post-norm, and I think this has been probably pretty much like evident from most of the papers nowadays coming out. Pre-norm like helps and the post-norm. So that is again like one similar analysis that they find. Next thing in this case, like there are other normalization like ways. So one is like RMS normalization, but they see that like even sophisticated normalization techniques have no gains like compared to like layer norm, pre-layer norm basically in this case. And pre-layer norm, the main advantage of why they go for pre-layer norm is to enable like larger learning rates. So you can use larger learning rates basically when you use pre-layer norms. And yeah, I didn't understand this. Like we see that limited benefits from including it by itself. So that's like something I'll have to maybe spend more time or at least check once. Yeah. And for just head block, so head block is something like basically just a linear head over the top. So in this case, if you look like they say that when you have the non-linear head, sorry, so when you just have non-linearity as well in the linear head, like the MLP layer, it doesn't make that difference. So you can just have a single like linear head like that, which would also result in same performance. Biases again, like you don't need biases. Next is like sparse token predictions, like as well as final layer norm basically at the end to stabilizer training as well. So that's like the architectural changes that they make in not changes but like modifications in the actual existing architectures just to speed up the gradient computation. So
So
is that
this
clear? Yeah.
is
Yeah.
this is for the multi-head block, for the just regular head block,
So
self-attention,
this
regular
is like
attention.
regular head block. So this is just a regular head block that you have. So let's say out of once you pre-train the network, right? You have the CLS token, right? And you use this CLS token and pass it through a head, right? Like a linear head. So this is talking about the same linear head, like adding a linear layer on top of the pre-trained BERT model. And like usually we try to add a MLP block, right, at the top, but that's not necessary. That's what the paper says in this case.
But wasn't the nonlinear head trying to fix like some problems that come later?
Mm. But there's no conv layer, right, in this case. Could you maybe try clarify once? So in this case, there's no convolutional layer, right? So maybe it was like that they add non-linearity. So maybe like let's say have like maybe fix some maybe let's say predictions in a way if possible, but probably as per their observations that it doesn't have much impact. So overall, if you have like because at the end of the day, right, if you see like in the pre-training one, that's where your representations would have be should have meaningful like so like once you pass a layer, let's say input through a pre-trained backbone board, right? That's where basically representation should like have the entire meaning, right, encoded. And basically linear layer would be just a layer for maybe doing the task specific like predictions, right? Basically given this representations that you have.
Just
So
a curiosity, you found this out like by trial and error, or you had a hypothesis?
so I think their hypothesis was that they just want to scale down, right? Like in terms of and study how much can they cram. And this is all the ablations and things that they carry out and they find this. So this all this is more empirical, right? Like trial and error and trying out. Not yeah, because intuitively it would seem that like you should have non-linearity, but yeah, it doesn't make much difference like when you go to the actual performance. So that's what they discover.
I mean, good job. That was pretty smart.
Yes. Yeah. And yeah, so now coming to the training, right? So in training, as we saw, right, or as I mentioned before, so we are just using the simple MLM objective in this case, and the same configuration of the mask like ratio of 15% as mentioned in the original board paper, with 10% mask filled with random words and 10% with the actual or same words, and we just mask 80% like words in this case, like so here, if we see like there was one paper, right, which I think, yeah, which showed that when you mask like higher, you see more performance gains. But probably in this case, like they see no improvements like when it comes to single day training. and like yeah, 40% there's no impact. Like, and if you have 40%, right, your gradient signals might be flowing more, and probably it would just increases more training time as well because of the computations backward. And later on in this case also they yeah evaluate the other objectives as such, but yeah, like they don't see any improvement. So instead of like just doing mass language modeling objective like basically just predicting the tokens, they also try to like do mean squared error. So like basically the error between representations and C. But yeah, that's also like no like doesn't lead to much performance improvements. And with the choice of optimizer, standard Adam optimizer works best, at least with very minimal changes. So you need weight decay of 0.01, and yeah, beta 1 and beta 2. I think in most of the literature of language model training, it needs to be zero point 0.9 and 0.98. If you have changes in beta values, it just changes the training and like messes up the training like very heavily. So yeah, these are the stable value like values for stable training. And yeah, include they include gradient clipping, and that's all. That's to optimizer setup that they use. And they do try like other or higher order optimizations as well as the first order optimizations, but they don't see much changes in the improvements. Like yeah, so there's no specific advantage of like using one optimizer or the other. Adam works pretty well out of the box. And yeah, so learning rate schedule. So in this case, they even on learning rate as well, they do try out different things, but at least based on what the empirical finding is, like a simple one cycle learning rate with maybe some peak value of 10e minus 3 leads to better performance on this case. So for example, when we go to, let's say, this plot, right, in terms of learning rate. So if you see different learning rate schedulers, right, so probably all of the learning rate schedulers nearly have similar performance at the end of the training, and almost like learning rate scheduler is more like linear with the model performance, I think. That's what, yeah, simple one cycle learning rate, so that's linear. And yeah, so if you see here in this case, the ones which are above, so they have low peak due to like no warm up or no cool down. And yeah, so in this case, there's no explicitly warm up like training steps in the start, which kind of increases the learning rate. And then basically there's a gradual decrease. And yeah, the ones which you see very smaller loss comparatively, they work better because of like warm up and cool down, maybe warm up at the start or cool down at the end. So if you see in the same plots as well. So that's one way of why, yeah, learning rates and probably, yeah, overall you won't see much difference, but probably, yeah, it would still make some difference. So that's one. Batch size, again, like micro batch size with accumulation, gradient accumulation. And they try 1536 for pre-training and 4032, 4032 for downstream performance. And yeah, they don't say anything specifically like how they arrive at the batch size. Maybe this is some ablation that they try and like find out the best optimal batch size. Like here. Any doubts or any questions? Okay, I'll move forward. And
Can you share that table again?
yes,
So this is for after 1 day training.
yes, yeah, this is out of 1 day training, I think.
Okay.
Yeah, but there is like more like yeah, this is a semi task, but there are more tasks as well like later on. And probably yeah, so this is like just 1 day training, right? So you have a lot to pack, like let's say in the model parameters, right? Uh, in this case, so probably if you look at like they don't apply dropout explicitly in the training pre-training phase, because again, yeah, the training data is relatively like very high compared to the compute, so that's like not efficient. Yeah, in this case, like dropout will again like just make it difficult for the model to learn and like increase the training time itself. Like yeah, so they just remove the dropout, but they introduce dropout during the downstream fine tuning. So that's one like basically thing to know. And apart from that, they experiment with other things such as length curricula. I don't know about this one specifically, to be honest. Token dropping is one. and finding out, but they don't find any gains as such. So yeah, so I think this is due to probably like when you just want to train everything in like 24 hours and your data is comparatively much larger than the compute. So yeah, having dropout doesn't make much sense as per the thing. And data set. So in this case, they try out three data sets. So one is the pile data set. Next is I think this books data sets plus Wikipedia, and third is C4 data set. And in terms of the improvements, they see the best performance when it comes to pile data set for downstream MNLI. And let's say the C4 data set, right? So it is a bit more noisier because it's accepted like common crawl data set. So and they don't try much pre-processing steps in this case, but at least if you try more complex, let's say pre-processing, then you still might be able to improve the performance further as well. And yeah, that's one. And let's say in order to avoid token switch, like let's say where there is no compression, right? So what they do is like they use the following formula. So they put a threshold of zero point 0.3 and multiply by the number of characters that are there available in the maybe input data or example, and they then calculate the number of tokens. If number of tokens are less than the sorry, if larger than the like t times this number of characters, then they drop those entries from the data set just to like avoid, yeah, just to like remove the uncompressed versions of the text. And yeah, sorting the like tokenized sequences by their like prevalence, so unigram prevalence makes sense, or at least helps. So the idea in this case is like the ones which are more likely or at least easier should be given first, and then this give. So it's somewhat like a curriculum scheduling in a way, if you see. And yeah, this has a positive impact, like as we saw. And yeah, batch sizes I mentioned, right? So and they also in this case increase the batch size. So they find that increasing the batch size at the end of the pre-training helps, and like going towards like they go start from I think 1536 and then they increase the batch size till at the end is like basically 4032. So that's one in this case. Apart from that, yeah, so in terms of fine tuning on glue, right? So the parameters on this they follow the same standard like learning rate procedure and everything. Okay. So okay, sorry, yeah, my bad. Wait. So this they use a different learning rate, and this is say that improves the performance further as well when we like basically for this particular models which are fine tuned. So you pre-train on a just single GPU day. So that's there. And if you look at the performance in this case, so the one which at the top shows the BERT like models completely like trained on like the standard vanilla BERT models like on TPUs. And if you look at the second, third, and the fourth in sections, those are the ones trained on like single GPU days. So if we look comparatively, when we go to cram board and cram board, so we see that the performance is merely similar or at least very similar when like it's fully trained. So 82 and here it's 83.2, and like your comparatively compute is much lower. So you see some like improvements as well, but more or less if we look at like larger picture, I would say it is very closer, but maybe not on par every time, right? Or at least like out doesn't outperform every time. You have to put it right. Yeah. In one case we see improvement like probably when we would train on A6000s, maybe because like more or less in more tokens, so that like per token efficiency leads to better performance. So as shown by the scaling laws as well as the chinchilla model. So yeah, that's one in this case. And if we look at the average scores, right, of the different tasks on different models, like we see, so board base, like the standard board model, it is 84, and glue task, I think glue score is 80.9. And other models also, if you see, their scores are very similar or comparable. Maybe for I think Cola, we see a bit of this like different scores, or at least the scores are too low comparatively. So yeah. And yeah, that's probably, I would say, all. And yeah, there are the ablations that at least tries to go over the same like what they try and like yeah not. So when they train from the original BERT data, what they see, they train from the uh, original training architecture. I think what they see, as well as the original training parameters, what the performance they get. So yeah, and then they try like minimal modifications in training setup as well as the architectures. They see some sort of jumps in the performance. And yeah, that's the gist of the paper. And yeah, it is an interesting paper, I would say, because yeah, it is more most important for at least us. Maybe yeah, because we don't have luxury of like big compute. So how can we like get good performance with all these settings? And yeah, someone has tried and explored all this like configurations, and yeah, we can just leverage those out of the box right away. Any questions? Aishwarya, if you're trying to speak, then you're on mute.
Oh, yeah, not right now. I mean, I think obviously the obvious extensions are how does this translate over to like the larger, GPT type models.
Mhm.
Um, that would be kind of one question. And also the other one is I know like I think the other large bottleneck right now with transformers is just number of tokens you can pass in. How much more efficient does these modifications to the transformer and so forth allow you to actually pass in like larger and larger pieces of
Yes, that's true. Yeah, one of the disadvantages or at least drawbacks for this work would be that they don't try explicitly on higher token sizes, like understanding how much can you pack as well, because their experiments or like studies are capped at 128 sequence length. So yeah, but still, yeah, that would be an interesting question to explore, I would say.
Yeah, I wonder why there isn't more research on that. I feel like it's an it's pretty obvious bottleneck, right?
Yes, there are some works I would say which
I
have
know I
some.
know there was Longformer a few years ago, but I haven't seen anything, at least nothing's caught my eye since.
So there is one work I would say which at least have partially shown that you can uh, pack more like let's say during the inference. So probably you train with shorter sentences, but then during the inference you can pack more. So Alibi paper, it's a positional encoding paper, and yeah, they have a different way of like uh, positional encodings, and which like makes it possible to extend it to very higher sequence length as well.
Is this the paper you just linked?
Yes, yeah. So essentially, the point being in this case that you train on shorter sequences, but still you can do inferences on larger sequences without like changing performances. Like so,
Oh,
that's
very
one of
interesting.
the.
Have you tried it out, or is it like public code?
I think. Let me just see. I'm not sure if the code, but I think there are implementations of it. Like maybe someone has tried before.
Oh yeah, I see it. Code and models.
Yes. Yeah, I think there are code. Should be out.
Yeah, we should cover this, or I'll give it a pass later
Yeah.
today.
This is a like interesting paper. I think if you want to cover it.
Mm. So it says that the Big Science Bloom uses this approach.
Yeah, Big Science Bloom uses this like yeah.
Does Bloom have a much larger token size limit as a result, or?
Oh, I think no, I think they also train I think with similar token size, but during inference you can like do like much larger inferences like sequences.
Got it, got it.
Yeah. So the point in this case is that you don't need to explicitly train on larger sequences specifically. What you can do is like you can train on smaller sequences, but then during the inference you can like use extrapolation and like basically just have like larger sequences and do inference.
This is pretty useful. How does this? Okay, I have to read the paper before I can comment.
Yeah. Yes. So maybe we can cover this paper I think in next session probably. Yeah, that would be useful and it is relevant in this.
Yeah, we should. We should. I guess my obvious next follow-up was like, how can you modify other, is this like easily can you, because I know for long former you were able to kind of add it onto any other model
Mhm.
architecture because it was just updating the way that transformer attention worked. I wonder
Yes,
if this is similar. Can you just like plug it into other model architectures or?
I think yeah, we can plug it into standard like transformers architecture. I think. I believe. Yeah.
Interesting. Okay, yeah. We can read it next week then. I'll give it a pass too. I can present.
Yes. Yeah. I also need to read a bit more on this, but yeah, that's fine.
Very cool.
And I think yeah, in terms of long form or big bird, right? So it's typically what they do is like they just have this different attention mask, right? Or like at least ways you calculate sliding window, like diagonal attention and random attention mask, right? And that's how you get this like, good, like can train, let's say, on longer sequences, but with same compute cost, right, as you do at let's say on 5 and 2.
Yeah.
So that's one. Yeah, yeah, probably yes. Yeah, yeah, you have a question.
Oh yes, sorry. So I know I'm new here, but I was just wondering, is anyone interested, I guess, in either reproducing some of the results from this paper or just kind of investigating this general topic more? So I don't know if that's ongoing.
Yes, I think we can do, right, because they have publicly released everything.
Okay.
So we can try and play around with the code as well. I think I believe there's a let me just find out. Yeah. Did you
Sure.
have yeah the
If any,
repository?
sorry, go ahead.
Yep.
No, I was just gonna say if anyone's interested in doing more work on efficient training implementations or looking at the surrounding research relative to this, I'm very interested.
I was looking to the NEMO, like NEMO Megatron framework.
But I believe Nemo does sort of like kernel level. You need to write CUDA kernels, right, specifically for those.
Yes.
Yeah, so that's like yeah one. In this case, I think this paper doesn't like go into that path at all. It just like tries to rely on standard things in there. But I think yeah, definitely you get much better improvements on the gains when you go to a bit more low level.
Just a quick comment, but the challenge is like not only finding more efficient ways, but find efficient ways that are good for production.
Mm-hmm.
And then training people working on your team on how to implement that.
Mm-hmm. So in terms of I think in industry or at least production, right? People typically don't tend to deploy this bigger models, right? They just like distill this maybe expert models and like into very small model and just go for those, right? So I think that's a different, but I think yeah, that's like equally important. I would say maybe maybe Aishwarya might be better in a position I think to comment more on those.
Sorry, comment on what? I missed that question. Can you repeat
Yeah.
it?
So I think probably the question from Renan was that like exploring also how these models can be effectively and efficiently deployed in production is also an important question.
Ah, yes.
Yeah. Yeah. So probably I think you might be dealing with more of bigger models, right? So probably yeah. Since you're working maybe
Yeah. I
maybe
mean,
more
there's
in
been a lot of changes recently, right? Like I know Hugging Face has its own model inference API hosting system. I think a few others do too. So you don't really have to do everything yourself. I think the approach I had taken was actually, use AWS and everything, but
It's a little
open to
more
any
complex than that.
experience. Sorry, go ahead.
Okay, my experience with the Hugging Face API thing is that it's cool if doing a demo, but it's not really good if you have like a full-fledged product.
Got it. I see. Why is that?
How so?
It costs too much. It's very expensive.
Trust me, even hosting anything yourself is pretty expensive.
Well,
Yeah.
my experience also is that you increase performance by using gRPC, but most cloud providers don't support gRPC. So then, like, this gets so hard, like when I'm trying to bring to production.
Interesting. Um,
What is BRPC? Could you like just maybe like give a brief summary? I'm not very well versed.
So gRPC was invented by Google. It's just an RPC protocol for microservice, but like it's just better for inference. Like it reduces the latency of how you orchestrate all the microservices. So when you pick something like this and put on a Kubernetes,
Mm-hmm.
you wanna reduce latency. So your
Mm-hmm.
inference is quick, fast, so you save money on the inference because you have to spool up the cluster, do the processing, and that costs money per inference.
Mm-hmm. I see.
Wait, but how like at least in my experience, right? I don't think the gRPC versus no gRPC is really a significant time difference as opposed to just your cluster size or like your instance size and the number of CPUs you run it on, right?
There
Like
is
it's
an
not nearly.
AWS blog article which explains that. I just have to find it again. Yes, you're right. For smaller models, or depend how the big is and how much inference they're doing, yes, there's no big difference.
Yeah.
Also, it'd be cool if we could just hop in, I don't know, maybe Google Data Labs or Colab. I don't think Colab can work in group. SageMaker, we could do like a live code, code together, maybe a jam.
Yeah, what would you have in mind to actually code together?
Do you guys wanna do it?
Sorry, what would you have in mind to actually code together though?
I don't know. Just, what do you want to do?
Okay. Yeah, I mean if anything comes up, we're open to it, but um,
I mean, what I like is like when you get a small model like this, I don't know, 80 million parameters, 200 million, they might not be like, I don't know, as like Bloom, right? But doesn't matter. If you distill it and apply some graph theory, it can outperform the larger models.
Yes, but I think also one more thing, right? So if you have this sort of everything statically compiled, right, like in a graph, then probably the operations are much more optimized and you get bit speed ups as well there, right? When you during the inference.
Yes, and they just work so great, and like you don't need to have a model that knows everything about the planet.
Mm-hmm.
You just need a model that's good enough to do the task that you want it to do in the end. And then just this process of tweaking the data and doing the graph and apply the theory to make it optimal for the task you want. I think that's the real art.
So I'm just saying, like, probably do you see much gains when let's say you just like compile like so currently let's say PyTorch, right? PyTorch has this dynamic graphs, right, in a way. So it's using either like execution or lazy loading, right? So whereas compared to TensorFlow, they have this static compilation of the graph, right, in before the run. So you have already known, right, what input and output would be and what these shapes and everything. So they do optimization the actual compilation process itself, right? So do you see like much gains over there, or probably those gains are much not much significant?
Well, yeah, that's true in the training. But I was not thinking of training. I was just thinking on
No,
applying.
no. So inference as well, right? Because once you export the smalls like in statically graph, right? Like let's say if it's PyTorch, right, then jitted version, then probably do you see like gains, or probably those gains are more or less irrelevant, like insignificant?
But when you already have the model trained, right, and you don't want to do fine tune anything, you can use the paper node to vector
Mm-hmm.
and just do like a workaround, like just make a little bit more architecture, put different models working together, and then they do very well.
Okay, I see.
But that's duct tapery, okay? That's
Mm-hmm. See.
but like nice presentation. I appreciate like this is really cool. It's really cool you guys carry these meetings.
Yeah, like at least, yeah, the main reason for presenting this was like more that this is more a general problem for, let's say, the academic researchers or at least like independent researchers, which don't have access to this big compute. So how can they then just use this? So yeah, wanted to go over this and maybe see if we have something in plan or at least yeah, overall it might help someone one way or the other way in their day-to-day workflow. So I think yeah, that's
I
good.
think maybe a good extension would be to adapt this to like a model that someone's working on.
Mm-hmm.
Like
Yeah.
otherwise, sorry, go ahead.
Sorry, go on.
No, that was it. That was just if we
Yeah.
want to do like a live coding approach or something.
Yeah, I guess yeah, we might be. So in like where I'm working right now, so we might be planning to train some models. So we might try out this whole idea, like at least the ones, uh, like the suggested like tricks that are there. Because I think yeah, this might be useful, like probably, and yeah,
Yeah.
and maybe I will report like see if we actually then see this, let's say, thing to be reflected in other task as well, or probably just more of one like MLM based objective and like that's it. Because yeah, this has not been tried on language modeling like the auto-regressive language ones, which are at least like more prominent or like or less much more a bigger research space out in I would say. So yeah, it would be interesting to see what if all this holds there as well or not.
That sounds more like a research paper in and of itself.
Yeah, yes, yeah. So I think that's one. Also, how do you extend like to larger sequences? That's also another like thing.
hmm
Yeah.
Yeah, makes sense.
So for next week, are we covering then the alibi paper or?
Yeah. I think I can do that if everyone. Oh, actually, no, sorry. I will not be here next weekend, so someone else would need to cover. Actually, I will be out of town, so I won't be able to attend.
I see.
Akash, do you want to do it or anyone else? Actually, I mean, we're open to volunteers. I think recently only Jay, Akash, and I have been presenting, but if anyone else wants to present for the week, please do.
Yep. And it can be like you can divide as well things maybe in a paper as well.
Yeah,
With
exactly.
present like method, one can present some other related works out there. One can go over the other sections as well, experimental details and like similarly. So yeah, please do sign up for if you're interested.
So just again, as someone who's pretty new here, what is the process generally for presenting? Do you guys have a queue of papers that already exist, or
We've tried that in the past. Right now, it's more we just decide the week before what we're doing next week.
okay.
Sometimes there's enough that we want to read that it ends up being like, a plan for the next 3-4 weeks. But um, yeah, just due to schedules and having new papers come out all the time, it's hard to really plan too many months in advance. So yeah, I mean, we can change the process, but for now, it's mostly just
Yeah,
as
no,
we
I think
come up with papers, we just yeah.
Also,
yeah,
sometimes we just discuss code. So if you want to try, experiment with the paper that we just discussed, and we can just do some experiments with the code and then present them next week. That's also possible.
okay, awesome, yeah.
Yeah.
No, I think that's a great approach. Who should I kind of, if I'm going to stay in touch with somebody, either about a paper I'm reading or I guess some progress making on an example? Um, should I just, I
Yeah,
guess, the three of you guys?
yeah. I'm also interested in recreating this paper. And if you want any general update, you can just message in the group.
Yes, I
Okay,
was also interested if you want to maybe take this up further and like yes, try as a group and see reproducing the same results.
But you said that all the code and experiments are already
Yeah,
up, right?
yeah, code and experiments are up, so maybe we can try similar ideas for autoregressive language models, right? With GPT style models and see what works there, right? Building on top of this. Because it's a single GPU, I think 2080 Ti is still pretty cheap, I think, comparatively.
Yeah.
Definitely. Let me know however I can help. I
Yeah,
think
feel free to start a channel in our main group, and then a thread, and then we can
Sure.
obviously
Yeah,
just
yeah. Because I think in terms of compute, we might get support from like MLC as well if we have something planned. Maybe dedicated, then yeah, tentative to show, then probably yeah, that would be better. But yeah, if we want to take it forward, then yeah, it would be interesting.
right. No sounds good.
Yes. And
This
for
is something. Yeah, very good.
yeah, sorry, go on. Sorry, I didn't follow the last part. Could you
No,
repeat?
it's cool that people are like actually bringing up the wanting to work together on projects. I think what we can probably do next time is there's a few that I've also been kind of working on. We can try to create a list of all the project ideas people have, and then kind of group together on ones that we find interesting. That could be fun. I mean, in the past, it's just that this requires a little more coordination and effort by everyone, but given that everyone's interested and equally kind of invested in trying things out, we can give it a shot. 'Cause I think this is a great time, obviously, to be exploring this. So.
Yes. Yeah. And at least this is like something many people won't be exploring, I would say, still. Because, yeah, like the general perception of the community is that scaling up is only better. So, yeah. So this might
Yeah, let's
be.
do it. So I can do this. I'll start a Google Doc and put up all of the kind of ideas, proposal, whatever, and work I've done so far on a few of them, and then everyone else can chime in on kind of related things. And then maybe next week after the I won't be here. But next, like one of the following weeks we can go through them and kind of discuss. I think that would probably be the best way to structure it so that everyone's thoughts are on a doc beforehand.
Yes.
And it could also be a good way to kind of give each other feedback on issues, or just open questions.
Yes,
Sure.
sure. That would itself help more brainstorm the ideas as well, right? And maybe make it more like properly defined or like, yeah, if there are any more robust as well. Maybe. So, any new signups for next week's presentation, or at least anyone who would like to present?
So as for me, I already promised one of the other groups that I present for them pretty soon. So I think maybe I'll just once we got an idea of, I guess, something related to this sort of efficient training. Once I kind of like can identify another paper or something that the group would be interested in, I'd be happy to do it. And once I've read it, I can just let everyone know, and you guys can stick me in somewhere.
Yeah, would anyone want to cover alibi or the paper that
Me and Akash can probably divide if like that works. Akash.
you can? Yeah. Sorry, I won't be here. I'm gonna. But yeah, if we can record, I will also follow up with like permissions on the meeting invite. I think I need to share that with you guys too.
Is that a nonlinear biases enabled input lengths model?
Yeah. Yeah, it looks like it's about 6 months old, give or take. So should be good.
Yeah, but this is like a good paper, I would say. It was like, yeah, like had like one big use case where Bloom being very big product where they have used this. So probably
Yeah. Awesome. I think we are over. But thanks all for the discussion. I think we had great turnout, so excited to see you all. And good presentation, Jay. Thanks.
Yeah, I tried to like just start the paper this time. Yeah, wasn't much like at the presentation ready. So yeah.
Yeah. Oh, actually, that's a good question. We can have a discussion on. I don't know what tool you're using. How are you doing this?
So this was done by like iPad, but typically I use Journal otherwise.
Journal. Okay.
Yeah, journal which like it allows you to annotate. So I typically like to present annotated papers because that is a bit more better way. At least according to me, like rather than like going into slides, but depends. So I've shared a link journal. So this is a cross-platform tool for PDF annotations. I typically use this one. Otherwise,
Very cool. Yeah, I think this could be better in the sense that when you put into a presentation, you can't really add in as many details, right? Because you're kind of, rewriting a lot of it and the slides become dense. But
yes,
yeah, I'll try it out.
yeah, yeah. You can just like highlight and write things, so that's a bit more convenient.
Yep.
But yeah, we can try with both formats and see which ones people are more comfortable and like maybe stick with those with the same like later on.
Awesome.
Do you think it will be better to have presentations so that we can upload them somewhere later?
But we can upload this